Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in. Today we're going to go through an application of indices called binary or base 2. This is actually what computers use, so it's very useful if you want to do anything with computers. So firstly, we'll contrast it with our system. So the system that we use for arithmetic and representing numbers is base 10. So we need to represent heaps of different numbers so people know what you're talking about. You might want to say how much money you have, how many people in your class, whatever. Imagine if we had a different symbol for every number from like 0 to 1,000,000. My God, that'd be too hard to remember, 1,000,000 different symbols. So we've simplified our system. What our system, base 10, has is 10 symbols. Base 10, 10 symbols. We use the symbol 0, 1, 2, and we go all the way up to 9. So all the numbers that we write are combinations of these 10 symbols. So we do that for simplicity. So we don't have a different symbol for each number. So how then, if we only have 10 symbols, are we going to write a number like 1,000,000? Well, we arrange the numbers in columns. So for whole numbers, we have our first column is ones. And now 10 to the power of 0 is 1. Our next column to the left is 10 to the power of 1, which is tens. Then 10 to the power of 2 is hundreds, and then thousands, and so on. They can go on forever. So if I write a number like this, 1024, for example, it's the number 1024. It's 1,000 plus 2 tens plus 4 ones. So we can write it like this. That's how we write it in expanded form that you would have done in year 7. So we can represent any number just using these 10 symbols. For bigger numbers, we use different columns. So what about base 2 or binary? Well, it's the same sort of idea, except in base 2, there are only 2 symbols, 0 and 1. So your computer, to code things, just uses a whole heap of zeros and ones. And it has usually things that can convert it. So like if you're listening to an MP3 file, it's a whole heap of zeros and ones, and what the computer or the iPod or whatever has is some converter that converts that code, that number, to an electrical signal that makes a noise, and all of those noises end up making your music. So it's just a whole heap of zeros and ones. So you can actually represent any base 10 number with a base 2 number. There's a 1-to-1 correspondence. If you like, they're paired up, base 2 numbers and base 10 numbers. So they do exactly the same thing. In base 2, we want to represent really large numbers as well. So we use the column system again. But instead of having ones and then tens and then hundreds, we have ones. Then the next column is twos, the next column is fours, and the next column is eights. We only use the symbols 0 and 1. We can't write a number in binary like that. That doesn't make sense. The only symbols that we use are 0 and 1. So let's say I have this number here, 1101. Okay, so please read it like that, 1101. It's not 1101. So what number would that equal in our system? Well, that would just be, we do it in expanded form like this. It's 1 lot of 8, because 2 to the power of 3 is 8. And then we add 1 lot of 4. There's no 2, so I don't need to write that. And then we have a 1 on the end. So that number is 8 plus 4 plus 1, which is 13. So the number 13 in base 10 is represented like this in base 2. So we don't get confused, what we usually do is write a little 10 here. That means 13 in base 10, and we put a little 2 here. That represents that the number is in base 2. And that's how binary works. So let's look at a few more examples. So let's look at this number here. So this is 11111. 5 ones. Okay, so I put the little 2 to make sure you know that it's in base 2. It's not the number 11,111. That's a base 10 number. So what would this be? Well, the first column is ones, second column is twos, fours, 8s, and 16s. So this would be the number 16 plus 8 plus 4 plus 2 plus 1. That is the number 31 in base 10. So how might we add? We'll just look at adding numbers in binary. Well, it's actually very, very similar to how we would do it in base 10. So let's say I want to add these numbers in binary. Okay. So we're going to do a very, very similar process to what we do in base 10. So we start from the rightmost column. We go 1 plus 1 is 2, right? But we can't have a 2 in binary. We can only use the symbols 0 and 1. So what we do, similar to what we do in base 10, 1 plus 1, we would write, if it was 10 in base 10, we write a 0 and carry the 1. So now we have 1 plus 0 plus 0, which is 1. 0 plus 1 is 1. Sorry, I should have put the plus there. And then 1 plus 1 at the end. We can't write a 2. Instead, a 2 is written in binary as 1, 0. So 1001 plus 1101 equals this, 10110 in binary. Okay, let's just double check that this works in base 10. So this number 1001 would be 1, next column's 2s, 4s and 8s. So 1001 is the number 9 in base 10. So the number 1101 has an extra 4. As I've done that before, that is 13 in base 10. So the answer we get should be 22, but in binary. So there's no 1s. So there's 0 there. So this is a 2, a 4, there are no 8s, and there's a 16. So 16 plus 4 plus 2 does equal 22 in base 10. So we are right. We have done something right. So note, if the number ends in 0, then it will be even in base 2, and if it ends in 1, it will be odd in base 2, just like in our system. All right, hope you've enjoyed this video and learned something new. You can now go use this with all your computers. This has been the luckiest maths teacher in the world. Have a great day.